If you look up at the moon tonight, you'll see something both familiar and strange. Familiar, because you've seen that same face countless times before. Strange, because no matter when you look, it's always the same face. The craters, the dark patches, the outlines, they never change. The moon seems like a loyal friend who never turns their head. But here's the catch. The moon is spinning. It rotates on its axis just like Earth does. So why do we never see the far side? Why does our cosmic neighbor feel like it's locked in a permanent stare? The answer is one of the most beautiful examples of nature's invisible choreography, tidal locking. But before we dive into what that means, let's think about why this feels so counterintuitive. We're used to the idea that if something spins, different sides will eventually face us. You spin a basketball, and in seconds you've seen all of it. You turn your head, and the world around you shifts. So the moon must be breaking some rule, right? Not exactly. The moon is obeying the rules perfectly, but in a way that's easy to miss unless you picture it in motion. Imagine you're walking in a circle around a friend while holding eye contact the entire time. To keep looking at them, you have to slowly rotate your body as you walk. If you time your rotation just right, one full spin for every full lap, you'll always be facing them. This is exactly what the moon does with Earth. One rotation on its axis for every single orbit it makes around us. This one-to-one match is what we call synchronous rotation. But here's the real question. How did it get that way? After all, the moon didn't just decide to lock its rotation to its orbit. Billions of years ago, it spun much faster. And then, over unimaginable timescales, Earth's gravity started to interfere, not just pulling the moon toward us, but stretching it slightly. This stretching created tiny bulges on the moon, like subtle hills. As the moon rotated, these bulges were constantly pulled back toward Earth by gravity. That constant tug acted like a brake, gradually slowing the moon's spin. You can imagine it like dragging your hand through water. The resistance builds and your movement slows. Eventually, the moon's rotation slowed enough that its spin perfectly matched its orbit. Once that happened, the gravitational tug reached a point of balance and the locking became permanent. But there's a deeper layer to this. The moon isn't perfectly round. It's slightly elongated along the Earth-Moon line. That elongation keeps it stable in its locked position, like a key fitting snugly into a lock. If it tried to rotate faster or slower now, Earth's gravity would pull it back into alignment. This is why the moon's far side, often called the dark side, though it gets just as much sunlight as the near side, remains hidden from direct view here on Earth. And no, the far side isn't completely unknown to us anymore. We've mapped it with spacecraft, and it's fascinatingly different from the near side. Far more craters, thicker crust, and fewer of the dark lava plains we see from here. But to the human eye standing on Earth's surface, it's still invisible. Nature's own backstage. What's even more fascinating is that tidal locking isn't rare. It's the rule in much of the universe. Many moons in our solar system are tidally locked to their planets. Even Pluto and its largest moon, Charon, are tidally locked to each other, meaning they both always show the same face to the other. If you lived on Pluto, Charon would hang motionless in the sky, never rising or setting. Now, here's something that might blow your mind. Just as the moon is tidally locked to Earth, Earth's rotation is gradually slowing because of the moon's gravitational pull. It's incredibly slow, milliseconds per century. But given enough time, Earth could become tidally locked to the moon too. If that happened, one side of Earth would always face the moon, and the other would never see it. But don't worry, that won't happen for billions of years, long after the sun has changed our planet forever. Let's make this even more intuitive with a simple analogy. Imagine you're holding a heavy shopping bag by a string and spinning it around you. As you spin it, the bag tugs back on your arm. If the bag were squishy, the contents would shift slightly each time it tried to turn, and you'd have to pull it back in line. Over time, the resistance would settle into a rhythm where the bag always points the same way relative to you. That's tidal locking in action, except in space, the bag is the moon, the arm is gravity, and the timescale is billions of years. Here's another fun twist. Even though we only see one face, we actually see a little more than half of the moon over time. Because the moon's orbit isn't a perfect circle and its rotation isn't perfectly uniform, it wobbles slightly. This wobble, called libration, lets us peek around the edges, about 59% of the moon's surface in total. It's like the moon is occasionally leaning in and saying, "Want to see a bit more?" The beauty of tidal locking is that it's a reminder of how patient and precise the universe can be. It's not a sudden dramatic event. It's a slow, graceful dance where two bodies eventually find perfect synchrony. And once they do, that harmony can last for billions of years. When you look up at the moon tonight, you're seeing the result of an ancient process that's been frozen in place for longer than humanity has existed. The moon's steady gaze is a story written in gravity, inertia, and time itself. And it's still unfolding, not just here, but all across the cosmos. What's amazing is how this simple gravitational dance shapes not just what we see in the night sky, but also the way we think about celestial bodies. For centuries, people assumed the far side of the moon was a place of mystery, maybe even a completely different world. Poets imagined it, philosophers speculated about it, and until the space age, it remained pure guesswork. Only in 1959, when the Soviet Luna 3 probe sent back the first photographs, did we finally see that hidden hemisphere. And the surprise was immediate. The far side looked nothing like the moon we knew. It had far more craters and almost none of the large dark plains we call Maria. That difference is still the subject of scientific investigation, but one strong theory is that the Earth's gravity influenced the thickness of the moon's crust, shaping how its surface evolved. It's a reminder that tidal locking isn't just about rotation. It can subtly affect a world's geology over billions of years. Now, let's zoom out and realize something profound. Tidal locking is one of the universe's most common outcomes. In the solar system, most major moons are tidally locked to their planets. Even Mercury for a while was suspected to be fully locked to the Sun. Turns out it's in a more complex resonance, but the principle is similar. And here's where it gets even more mind-bending. Tidal locking also plays a huge role when we look beyond our solar system. Many exoplanets orbiting close to their stars are likely tidally locked. That means one side of the planet is in perpetual daylight, baking under constant starlight, while the other is locked in eternal night, freezing in darkness. If life exists on such worlds, it might thrive in the twilight zone between the two extremes, a thin strip of perpetual sunrise or sunset. The same mechanism that keeps the moon's face fixed toward us could be shaping the habitability of alien worlds. So, tidal locking isn't just a quirk of our moon, it's a universal process with deep implications. Now, let's return to Earth for a moment. The moon's locking to us affects our tides, our length of day, even our planet's stability. Without the moon, Earth's axis might wobble much more over time, causing extreme swings in climate. The steady pull of the moon helps keep our planet's tilt, and therefore our seasons, relatively stable. In a way, the same gravitational handshake that froze the moon's rotation also acts as a gentle stabilizer for our world. And here's a fascinating twist. We're not just shaping the moon's rotation, the moon is subtly reshaping ours. Earth's rotation is slowing by about 1.7 milliseconds per century due to tidal friction. The moon is stealing tiny bits of our rotational energy and drifting away from us at roughly 3.8 centimeters per year. It's not fast. You wouldn't notice it in your lifetime, but it means the moon is slowly growing more distant. Over hundreds of millions of years, this could change the way the moon looks in our sky, make solar eclipses less perfect, and alter the tidal patterns on Earth. The system is dynamic, even if it feels frozen in place when you look up at night. And that's the real beauty of it. The moon's steady gaze hides an ancient story of motion, friction, and gravitational balance. What seems still is actually the result of a long, slow struggle for equilibrium, a struggle that ended in perfect synchronization. If you want one final way to picture it, think of two dancers on an ice rink. One is much larger and heavier, the Earth, and the other is smaller, the moon. At first, the smaller one spins freely while circling the bigger one. But over time, their grip on each other changes the way they move, until they find a rhythm where each step and turn matches perfectly. Once they lock into that rhythm, the smaller dancer always faces the larger one, forever keeping their gaze fixed. That's the moon and Earth, a partnership millions of years in the making. And now, every time you look at the moon, you can remember that you're seeing the result of that ancient dance. You're not just looking at a rock in space, you're looking at a relationship. A gravitational bond so strong and so patient that it literally shaped a world. The far side will always be there, hidden from our direct view. But the fact that we never see it is a testament to the quiet, precise work of the universe's most persistent sculptor, time. And here's the kicker. Now that you understand this, you'll never look at the moon the same way again. That familiar face will feel like a secret being shared just with you. A reminder that even the most constant things in our lives can have stories of incredible change behind them. If you've enjoyed uncovering this hidden truth about our closest cosmic neighbor, Imagine how many more wonders are waiting to be decoded. That's exactly what we do here. Turn everyday observations into keys that unlock the bigger picture of how the universe works. So, like this video, share it with someone who's ever wondered about the moon's gaze, and subscribe to how it actually works. Because once you start seeing the world through the lens of curiosity, you'll find that everything, yes, even the moon, has another side.